think for a moment about all those unseen forces shaping our world, like flipping a light switch or that pull from a fridge magnet. It feels almost like magic, right?
It does, but it's all grounded in physics.
Right.
Really fundamental stuff.
Exactly. And today on the deep dive, we're tackling electromagnetism. We're digging into some great sources you shared with us. Okay, let's unpack this.
Absolutely. We've got some really rich material here covering the core ideas, and our goal really is to make these concepts clear, maybe find a few surprises along the way for you.
Yeah.
We'll look at how current causes magnetic effects, electromagnetic induction, and things like transformers that you use every day. The mission is to boil it down for you.
Perfect. We want those aha moments,
Yep.
that click where you really grasped this corner of physics. So electricity and magnetism being connected, where did that idea even start?
Okay, so a really key moment was back in 1820, Hans Christian Oersted's experiment. That was kind of the initial spark, you could say.
The spark. Right. So picture this. Oersted just had a wire hooked up to a battery, a basic circuit, and nearby, sort of by chance almost, there was a compass. What happened was pretty revolutionary, wasn't it?
It really was. Before his eyes, well, with no current, the compass just pointed north-south, normal behavior.
Sure. Earth's magnetic field.
Exactly. But the second current flowed in that wire,
Mm-hmm.
the needle.
Hmm.
Well, it jumped. It deflected. Specifically, current going south to north under the wire made the North Pole swing west.
And it wasn't just a tiny flicker, was it? The sources say if he increased the current, the deflection got bigger.
That's right. A very direct link. And there was more. He reversed the current flow. The
Right.
needle swung the other way, to the east. And if you put the compass above the wire, the deflections were opposite again.
Wow.
This one experiment just completely shattered the old idea that electricity and magnetism were separate things. It basically paved the way for, well, electromagnetism as we know it.
Mhm.
Modern physics depends on this.
So a clear pattern. Electricity was definitely messing with magnetism in a predictable way. What was the big takeaway from all that?
The core idea, the inference, was huge. Electric currents produce magnetic fields. That was the first real proof of a deep connection. The fundamental point, like our sources really stress, is that moving charges in the electric current is moving charges they inherently create magnetic fields around them.
Okay, current makes a magnetic field. But it's invisible, right? How do we even picture that? That's where magnetic field lines come in, yeah.
Precisely. To help us visualize this unseen force, we use the idea of magnetic field lines. There's a classic experiment for this, iron filings.
Ah, yes.
You take some cardboard, poke a wire carrying current straight through it, and then sprinkle iron filings on top.
And what do the filings do? I hear it's quite a striking pattern.
It is, yeah. You pass current through the wire, maybe tap the cardboard gently, and those little iron filings just snap into place. They form concentric circles around the wire,
Concentric circles.
centered on the wire and perpendicular to the wire.
So the field isn't just a vague cloud, it actually has this, circular structure. What happens if you change the current direction? Do the circles change?
The circular pattern stays, but the direction of the field lines flips. If you used a little compass, you'd see its needle point the other way around the circle.
Okay.
And just like Oersted saw, more current means a stronger field. Visually, the circles of filings get denser, packed closer together, and they spread out further from the wire.
You mentioned the Earth's field earlier. Our sources say that plays a role, too. How does that fit in?
Right, good point. What you actually see is the combined effect, the field from the wire, and the Earth's own magnetic field. Close to the wire, its field is usually much stronger, so you see the circles clearly.
Makes sense.
But further away, the Earth's field starts to take over more, and the pattern gets less clear. And there can actually be points called neutral points, where the wire's field and the Earth's field exactly cancel each other out. Zero magnetic field right there.
Okay, concentric circles. Got the picture. But pulling out a compass every time to find the directions seems a bit fiddly. Is there a quicker way, a rule or something?
There is a very handy one. It's called the right-hand thumb rule, or sometimes the right-hand grip rule.
Ah, the classic. Walk us through that. How does it work?
Okay, imagine you grab the wire with your right hand, thumb pointing in the direction the conventional current is flowing that's positive to negative.
Got it. Thumbs up along the wire.
Exactly. Now look how your fingers naturally curl around the wire. That direction, the way your fingers are pointing, that's the direction of the magnetic field lines.
Oh, okay. So current going up means my fingers curl anti-clockwise around the wire. That's neat, simple, and effective.
It is a really quick way to figure out the field's direction. No compass needed.
Right. Now that's for a straight wire. What if we bend the wire? make it into a loop. How does changing the shape change the field?
Excellent question. When you form a wire into a loop, yeah, the magnetic field gets more complex, but also uh, more interesting in some ways. If you did that iron filings experiment again, but with a loop through the cardboard.
Different pattern, I assume.
Definitely. Near the wire itself, the lines are still sort of circular, following the wire's curve. But inside the loop, something cool happens. The field lines all tend to point the same way. And near the very center, they become almost straight, parallel, and quite uniform.
Parallel in the middle. That sounds very different from the spreading circles around a straight wire. What are the key things to understand about that?
Okay, so a few key points. One, inside the loop, the field lines generally point in the same direction. Two, right at the center, the field is pretty much uniform and points perpendicular to the plane the loop sits in.
Okay.
Three, you can make that central field stronger by either pushing more current through the loop or by winding more turns of wire, making a coil instead of just a single loop.
More turns, stronger field. Makes sense.
And maybe the biggest point, a current-carrying loop acts like a magnetic dipole. It has a north pole and a south pole, just like a little bar magnet.
Like a tiny magnet. How can you tell which side is north and which is south?
There's another rule for that. It's called the clock rule. Pretty intuitive.
Yeah.
You look at one face of the loop. If the current is flowing around anti-clockwise when you look at it, that face is the north pole.
Anti-clockwise is north. Okay.
If the current is flowing clockwise, that face is the south pole.
Clockwise, south.
Okay.
So the current direction totally determines the magnetic polarity. That's fundamental. Okay, let's stretch this idea. What if we take that loop and make it long, like a cylinder made of wire coil?
A solenoid, right?
Exactly. A solenoid is just a long coil, usually longer than it is wide. And the magnetic field from a solenoid is really distinctive and incredibly useful if you did the iron filings test again.
Let me guess, another unique pattern. You got it. This time, the pattern looks remarkably like the field around a standard bar magnet. It's almost uncanny. It's like we've built our own magnet, just using wire and electricity, and one you can switch on and off.
So what does the field look like inside and outside the solenoid?
Inside a long, tightly wound solenoid, the field lines are almost perfectly straight, parallel to the axis, and evenly spaced. This means the magnetic field inside is strong and very, very uniform.
Uniform inside, okay.
Outside, the field lines loop around from one end to the other, much weaker and more spread out, just like a bar magnet's field. And again, you make the field stronger by increasing the current or packing more turns of wire into the same length.
The sources also mention putting something inside the solenoid. A soft iron core. What does that do?
Ah, yes. Putting a core of soft iron inside the solenoid makes a huge difference. It dramatically boosts the magnetic field strength. Soft iron has what's called high magnetic permeability, meaning it gets magnetized very easily. The solenoid's field magnetizes the iron, and the iron then adds its own strong magnetic field to the solenoid's field.
Yeah.
The overall effect is much, much stronger. Think of it like an amplifier for the magnetic field.
And does the solenoid also have north and south poles? Like the loop?
Yes, absolutely. And the same clock rule applies. Look at one end of the solenoid. If the current seems to be going anti-clockwise from your viewpoint, that's the north pole. Clockwise means it's the south pole.
So a solenoid with current acts a lot like a bar magnet. What are the key similarities the sources point out? And maybe more importantly, the differences?
Well, the similarities are pretty clear. The field pattern looks almost identical. If you hang them up so they can swing freely, both will line up north-south with the Earth's field, and both attract iron bits.
Okay. And the differences?
The differences are where it gets really interesting. With a solenoid, you can change the strength of its magnetism just by adjusting the current. Can't do that with a bar magnet. Its strength is fixed. And even cooler, you can flip the solenoid's north and south poles instantly just by reversing the current direction. Try doing that with a regular magnet.
Huh. Good luck. This ability to control it. That leads us straight to electromagnets, doesn't it? That adjustability sounds incredibly useful. What exactly is an electromagnet?
An electromagnet is basically a temporary magnet, but it can be a very strong one. It's made by passing current through a coil wrapped around a core, usually soft iron. The key word is temporary. The magnetism only exists while the current is flowing.
Turn off the current, turn off the magnet.
Precisely.
And they come in different shapes. The sources mention I-shaped and U-shaped ones.
Yeah, those are common. The I shape is just a straight bar core with a coil, like a solenoid with a core inside. The U shape, or horseshoe electromagnet, uses a U-shaped core. Winding coils on both arms concentrates the magnetic field in the gap between the poles. Makes it really strong right there.
So how do they work? What's the mechanism?
Well, the current in the coil creates a magnetic field, like we discussed with solenoids. This field magnetizes the soft iron core really strongly because of that high permeability we mentioned.
Okay, the iron boosts the field.
Right. But soft iron also has low retentivity. That means it doesn't hold on to its magnetism. As soon as you switch off the current, the iron loses almost all its magnetism instantly. That's why they're temporary.
And that on-off capability is what makes them so versatile. What are some typical uses the sources mention?
Oh, loads of things. I-shaped ones are often used in relays like electric switches. The U-shaped ones are crucial in DC motors, AC generators, electric bells, lots of common devices.
You mentioned DC motors specifically. Does the type of current matter?
Yes, absolutely.
Yeah.
For things where you need a consistent north and south pole, like in a DC motor, you need direct current, DC. If you used alternating current, AC, the poles would flip back and forth constantly, many times a second, which isn't usually what you want in a motor, though it's useful elsewhere.
Right. Makes sense. So electromagnets, temporary, controllable, potentially very strong. What about the other side of the coin, permanent magnets? What's the main difference?
Permanent magnets, well, the name says it all. They keep their magnetism for a long time. They're usually made of materials like steel, which has high retentivity. It holds onto its magnetism much better than the soft iron. Once it's magnetized, it stays magnetized.
So it's a trade-off then. The constant field of a permanent magnet versus the control you get with an electromagnet. What are permanent magnets used for, according to the sources?
You find them in places where you need a steady, reliable magnetic field. Things like electric meters, galvanometers, ammeters, voltmeters often use them. And of course, the needle in a magnetic compass is a small permanent magnet.
Our sources have a nice comparison table. Maybe we can quickly run through the main differences between electro and permanent magnets.
Sure. Material. Electromagnets use soft iron. Permanent magnets typically use steel. Magnetism. Temporary for electromagnets, only when current flows. Permanent for the others. Strength. Easily changed in electromagnets by varying current. Fixed in permanent magnets. Polarity. Easily reversed in electromagnets by reversing current. Fixed in permanent magnets. Strength potential. Electromagnets can generally be made much stronger. Demagnetization. Easy for electromagnets. Switch off current. Hard for permanent magnets.
That sums it up nicely. So the big advantages of electromagnets really boil down to that flexibility, don't they?
Exactly. Being able to create very strong field, being able to adjust that strength, being able to switch the polarity, and being able to turn the magnetism completely off those up. Those are huge advantages in many, many applications.
Speaking of applications, the sources list quite a few practical uses. Let's talk about some of those. Lifting heavy stuff.
Yeah, that's a major one. Huge electromagnets are used in scrap yards and steel mills to lift and move massive amounts of iron and steel. Scrap metal, girders, plates. We're talking tons. The sources mention some can lift like 20,000 kilograms.
Wow, that's incredible.
And the beauty is, to drop the load, you just cut the power. They're also used to load iron into furnaces, separate iron out from waste or ores in mining, and even for delicate things like removing tiny iron splinters from someone's eye or wound.
From giant cranes to surgical tools, that's amazing range. And you mentioned they're inside lots of electrical devices, too.
Oh, absolutely. They're fundamental. Electric bells, telegraphs, less common now, but historically important. Some electric tram systems, electric motors, relays, microphones, loudspeakers. The list goes on. They're everywhere in technology.
Let's zoom in on one of those, the electric bell. It's such a classic example. Can you walk us through how the electromagnet makes it work based on what our sources describe?
Sure thing. A standard electric bell usually has a U-shaped horseshoe electromagnet. Near it, there's a little piece of soft iron called an armature.
Armature. Okay.
This armature is attached to a springy metal strip, and on the end of that strip is a little hammer positioned right next to a gong. There's also an adjusting screw that the springy strip normally touches, completing the circuit.
Right. So when it's resting, the circuit is complete through that screw.
Exactly. Now, you press the button, the switch. This lets current flow from the battery through the contact screw, through the coil of the electromagnet.
Okay, current flows, electromagnet turns on. What next?
The electromagnet does its thing. It attracts the soft iron armature. This pulls the armature towards it. As it moves, the hammer attached to it hits the gong. Ding.
Makes the sound. Got it.
But as the armature moves towards the magnet, that springy strip it's attached to gets pulled away from the adjusting screw.
Ah, So it breaks the circuit,
Precisely. The contact is broken, the current stops flowing to the electromagnet.
and the electromagnet switches off.
Right. It loses its magnetism, so it stops attracting the armature. The springy strip then pulls the armature back to its original position
Where it touches the screw again.
and completes the circuit again. So current flows, the magnet turns on, attracts the armature, hammer hits gong, breaks the circuit, magnet turns off, spring pulls it back, makes contact.
And it just keeps repeating that cycle really fast.
Exactly. As long as you hold that button down, the cycle repeats over and over, hitting the gong, breaking the circuit, resetting, hitting the gong again. That's what creates the continuous ringing sound.
That's actually a really clever mechanism. Simple but effective. What if you used AC power instead of a DC battery? The sources mention that.
Yeah, it would still ring.
Yeah.
Because the attraction part doesn't really care if it's a north pole or a south pole attracting the armature, just that there's a magnetic field.
Okay.
But with AC, the magnet's polarity would be flipping back and forth very rapidly, 50 or 60 times a second usually. This would still pull the armature back and forth, but the sound might be different. Probably more of a continuous buzz than a clear ding-ding you get with DC.
Fascinating detail. It really shows how this basic principle, electricity making magnetism, plays out in everyday things.
We've certainly covered a lot of ground today, haven't we? From Oersted spotting that twitching compass needle
Yeah.
all the way to these powerful, controllable electromagnets lifting tons of steel or making a bell ring.
We really have. It's quite a journey when you trace it, seeing how moving charge creates these fields, how we learned to visualize them with lines, shape them with loops and coils, and then harness them with electromagnets. It's the foundation for so much of our technology.
Absolutely. So as you go about your day, maybe just notice all those moments where electromagnetism is quietly working behind the scenes, powering things, making sounds, moving stuff. Kind of makes you wonder, doesn't it?
Yeah.
What other invisible forces might be shaping things in ways we haven't fully grasped yet? Maybe this dive has sparked some curiosity for you to explore even more of the amazing world of physics.